ठीक है. So let's continue with this topic, that is AAC1. Okay. Before discussing this AAC1, let's quickly revisit AAC2. Okay. And that is acid catalyzed acyl oxygen bond breaking bimolecular. Okay. So this is a ester hydrolysis. So it is acid catalyzed, and during this hydrolysis, acyl oxygen bond is break, and it is a bimolecular reaction. Okay, so this reaction we have discussed in detail in previous lecture. So this is first ester. Now this reaction carried out in presence of acid. So acid we have already added in the reaction. So first this ester get protonated, gives a protonated ester. Now this carbon is electrophilic in nature, and we are discussing the hydrolysis, means we have used water as excess. So in water, this oxygen contains two lone pairs. One of the lone pair attacks on this electrophilic carbon. And what we get, this is an important intermediate which is known as a tetrahedral intermediate. Now this tetrahedral intermediate is a steric sensitive, because your carbon, which is earlier is sp2 hybridized, and this carbon is sp3 hybridized, and sp3 hybridized carbon is always steric sensitive. That's why this step is slow step, and it is a rate determining step. And if you observe, in rate determining step, two species are involved. One is protonated ester and another one is water molecule. That's why this reaction is a bimolecular. But if I talk about the overall order of the reaction, it is a pseudo first order reaction. It's not a second order reaction. It looks like a second order reaction, but it is not a second order reaction. Then what happened in next step? Proton transfer. So that we have discussed. Later on, this alcohol molecule is eliminated from the molecule and gives the protonated acid. And the final step is a deprotonation step and gives the acid. So when we hydrolyze the ester in presence of acid, what we get? Acid plus alcohol. And this is a forward reaction, is a hydrolysis. But when you look at the backward reaction, is a esterification. That's why the acid hydrolysis is a reversible reaction. Acid hydrolysis is a reversible reaction. Clear? So forward reaction is ester hydrolysis, but backward reaction is a esterification. And the second step in the both esterification as well as the ester hydrolysis is rate determining step. So here the second step, in case of ester hydrolysis, the second step is a rate determining step, which leads to the formation of tetrahedral intermediate. So second step is a rate determining step. So the rate of ester hydrolysis depends on the two species, ester and water. But here we have take the water in excess because we are talking about hydrolysis. So in the hydrolysis, we always use water in excess. So reaction is bimolecular, but when I talk about the order of the reaction, is a pseudo first order reaction. So reverse reaction is esterification, as I said earlier. Reverse reaction is esterification. Okay, it's also a bimolecular reaction. Then after we have discussed how we can increase or decrease the rate of ester hydrolysis or esterification. As I said earlier, the second step is a rate determining step in which tetrahedral intermediate is formed, and this tetrahedral intermediate is always steric sensitive. So if I increase the bulky group in the tetrahedral intermediate, of course, the formation of the tetrahedral intermediate get decreases. The rate of formation of tetrahedral intermediate get decreases. Hence, the rate of esterification or ester hydrolysis also get decreases. So if I increase the steric bulk in the ester or even in the acid, the rate of ester hydrolysis and esterification both are decreases. Because now the steric bulk is increases. Hence, the steric interest increases, the rate of esterification, even ester hydrolysis also get decreases. Okay, so that we have discussed in detail in previous lecture. So in this class, we are going to discuss another mechanism, that is AAC1. Okay, till now any confusion? Till now any confusion? Okay. So let's continue. What is AAC1? A stands for acid. AC stands for anyone? AC stands for acyl oxygen bond breaking. One stand for very good, it is a unimolecule. Okay, so before I'm going to discuss this AAC1, let me take the example of SN1. So where we have used a tertiary butyl chloride, and SN1 is a two-step process. What happened in the first step? This carbon chlorine bond is break and formed stable carbocation, which is then attacked by nucleophile. Now it attacks from the back side as well as from the front side. So here we get two different products. And in case of SN1, what we get? Racemic mixture. What we get? Racemic mixture. In case of SN1, the first step is a rate determining step. And this step is slow. So the rate of SN1 is only depend on the concentration of substrate. And we know very well that SN1 is only proceed in the molecule whenever the molecule is able to form a stable carbocation. The rate determining step involves only one species, that is a tertiary butyl chloride, and that's why this reaction is known as a unimolecular. So one thing is clear from this SN1, that unimolecular reaction is proceed through the stable carbocation in case of SN1. Okay, so molecule proceed to the SN1 whenever the molecule is able to form a stable carbocation. If it is not able to form a stable carbocation, then it will not form a product through the SN1 mechanism. So this concept we are going to use here, because we are going to discuss, that is AAC1. That means only those ester or acid proceed through the AAC1 are able to form a stable carbocation. So here we have to discuss about the stability of the carbocations, because this mechanism AAC1 is proceeds by those molecules which are able to form a stable carbocation. Because I'm talking about unimolecular reaction. Okay. So when I use a sterically hindered acids, because we know that this is a sp3 carbon, this is a sp3 carbon, and this is a tetrahedral carbon. Tetrahedral carbon is always sterically hindered. Okay. So when I use a sterically hindered acids like 2,4,6 trimethyl benzoic acid, this is a sterically hindered benzoic acid. And this is known as a 2,4,6 trimethyl benzoic acid. And this is also known as a macetoic acid. Another acid that is 2,4 dimethyl benzoic acid. So this is one. So here we have methyl group. Here we also have a methyl group. So this is known as a 2,4 dimethyl benzoic acid. Because both these acids are sterically hindered and are able to form a stable carbocation. Even if we have trialkyl acetic acid, so this molecule is also able to form a stable carbocation. This is known as a trialkyl acetic acid. So here I taken the example of trimethyl acetic acid. So all these three acids are able to form the stable carbocations. That's why the esterification of these three acids we can explain to this mechanism AAC1. Okay, so let me take the ester of this acid, macetoic acid, methyl macetoate. So this is a methyl macetoate. So when I hydrolyze this methyl macetoate by adding acid, in presence of water, because we are talking about hydrolysis. Now first, it leads to the formation of carbocation. And we are talking about AAC1, means acyl oxygen bond is going to break. So this bond is going to break and forms stable carbocation. So this is the carbocation is formed when I break the bond between acyl and oxygen. And this carbocation is known as a acylium ion. Acylium ion. And it gives methanol as a byproduct. Methanol as a So later on, this acylium ion combined with the water and gives the acid. Clear? So only those molecules proceed to the AAC1 are able to form a stable carbocation. So this carbocation is stable. Why this carbocation is stable? Because here oxygen has two lone pairs. Oxygen has two lone pairs. So when these lone pairs transfer here, the positive charge of this carbon get neutralized. So this carbocation stabilized by the lone pair of this oxygen. This effect is known as a mesomeric effect. And this carbocation also stabilized by this methyl group through the hyperconjugation. So that's why the hydrolysis of methyl mesitoate we can explain through the AAC1 mechanism. Similarly, if I have mesitoic acid, then discuss about the esterification of mesitoic acid. This mesitoic acid is also able to form a stable carbocation. So when I react this mesitoic acid into the of H2SO4, and now I am adding the methanol. So mechanism we will discuss later on, but this mesitoic acid also leads to the formation of stable acylium ion. And here the byproduct is S3O plus and HSO4 minus. So both these reactions we can explain through the AAC1 mechanism, because both these molecules, methyl mesitoate as well as the mesitoic acid, are able to form stable carbocations. So let's discuss first ester hydrolysis. Ester hydrolysis by AAC1 mechanism. So whenever AAC1 words comes in your mind, you have to always think about the molecules which are able to form stable carbocations. So I'm talking about ester hydrolysis, that's why I use methyl macetoate. We know that esterification or ester hydrolysis both are reversible reactions. Both are reversible reactions. So this is acid catalyzed. So in first step is always protonation. Whenever any reaction catalyzed by acid, the first step is always protonation. Now this oxygen has two lone pairs. Now one of the lone pair get protonated. One of the lone pair now get protonated. Let's see what happened. We get protonated ester. So one lone pair is still remain. And what happened? One of the lone pair is used for the protonation. That's why this oxygen become positively charged. And these three methyl groups remain as it is. So this is a forward step, and the forward step is known as a protonation. But what will be the reverse step or backward step? Backward step is a deprotonation. And the protonation and the deprotonation are always fast. This step is fast. This is also fast. Now what happened in the next step? Now this group is a good living group. Good living group. So it can easily leave from the molecule. So this bond, acyl oxygen bond, is now break, and the positive charge of this oxygen get neutralized. As a result, what happened? We get stable acylium ion. We get this ion, and by elimination of methanol, as we discussed earlier, the AAC1 mechanism, in which the first step, the formation of carbocation, is a rate determining step. So this step is also rate determining step. If you observe in rate determining step, only one species is involved. That is this protonated ester. That's why it is a unimolecular. Okay. So in the red determining step, only one species is involved. That is a protonated ester. That's why this mechanism or this reaction is a unimolecular reaction. And if I discuss about the reverse step, when the methanol again attacks here, we get this step. As a clear? So that's why this step is a reversible step. So this step is a rate determining step and it is a slow step. So the forward reaction is a slow step. But what happened about in backward reaction, where the methanol is now attacks on this positively charged carbon. So methanol is attacks on this positively charged carbon. We get this molecule, but this attack is fast. This attack is fast. So the forward reaction is slow, but backward reaction is fast. Fast. Is it clear? Is it clear? यहाँ तक किसी को कोई डाउट है? Is there any doubt till now? So first we have formed a stable carbocation. This is known as a this is very important intermediate, and this is known as a psyllium ion. Psyllium ion. Okay, now what happened in the next step? Now we have added already the water molecule. Because we are discussing about hydrolysis, that means water is always present in excess during the reaction. So again, this water molecule, this oxygen contains two lone pairs. Now one of the lone pair now attacks on this carbon. This is positively charged carbon. Let's see what it gives. Get this molecule. So here we have positive charge. Again, the one lone pair is used to form a bond between carbon and oxygen. That's why this oxygen become positive in charge. What will be the reverse step? So the attack of water molecule on this carbocation is always fast. Similar to here. So this attack is fast. Because here we also discussed that attacks of this methanol on this carbocation is fast. So this is a fast step. But what happened in the backward reaction? Water molecule is leave. If the water molecule is leave, we get this structure. But the elimination of water and the formation of the carbocation is a slow step. So this is a slow step. This is a slow step. In the slow step, what happened? Water molecule is eliminated. Water molecule is eliminated. Is it clear? Is there any doubt till now? Is there any doubt in the till now? Okay, fine. And last step, what happened? the positive charge of this oxygen get neutralized by elimination of the proton. So last step is a deprotonation step. And what we get? Acid. So in the backward step, what happened? Protonation. So this is a forward step. In backward step, this OH get protonated, we get this step. So the forward step is a deprotonation. Means elimination of H plus. And if you observe, the backward step is a protonation. Means addition of H plus. Whether it is a deprotonation or protonation, both are always fast step. Because this is a acid-base reaction. Okay. So this is the mechanism of ester hydrolysis of methyl mesitoate through the AAC1. Okay. So what happened in the first step? Whenever we have added the acid during the reaction, the first step is always protonation. So first this oxygen get protonated because this oxygen contains two lone pairs. One of the lone pair get protonated and gives the protonated ester. So the forward step is a protonation, but backward step is a deprotonation. And protonation and deprotonation steps are always fast. So after that, what happened? Now this is a protonated ester. Now this protonated ester contains a good living group. This is a methanol. Methanol is a good living group because it is a stable molecule. So it eliminates from the molecule and left behind the stable carbocation, that is acylium ion. So the forward reaction is elimination of methanol, and the formation of the carbocation is a rate determining step in this reaction. And this step is a slow. But what about the backward reaction? In backward reaction, what happened? This methanol attacks on this positively charged carbon, we get this molecule. But the attacks of methanol to this carbocation is a fast step. But the elimination of the methanol and formation of carbocation is a rate determining step. That is a slow step. I didn't say that it is a rate determining step, that's why it is a slow. Okay. It is a slow and rate determining step. I didn't say that it is a slow step, that's why it is a determining, or vice versa, that's why it is a rate determining, that's why it is a slow step. It is a wrong. It is a slow step and it is a rate determining step. Okay, because we have many reactions in which the fast steps are rate determined. So this is a formation of acylium ion from this protonated ester is a rate determining and the slow. Now what happened in the next step? The water molecule now attacks on this positively charged carbon and gives the protonated acid. This is nothing but protonated acid. And what about the backward step? In backward step, what happened? Water molecule is eliminated from the molecule and forms this acylium ion. So formation of acylium ion is a slow step. So that's why the backward step is a slow through the elimination of water molecule. And what happened in the last step? Deprotonation. This is a protonated acid. When it gets deprotonated, gives the macetoic acid. This is a macetoic acid. And this mechanism is AAC1. Acid catalyze, acyl oxygen bond breaking unimolecule. Acyl oxygen bond breaking unimolecular. Okay. So if you closely look at the ester hydrolysis of this methyl macetoate, forward reaction is a ester hydrolysis and the backward reaction is esterification. Any one can ask in the examination whether it's esterification or ester hydrolysis. Okay, and the second step in both this mechanism, the second step is a rate determining step. Rate determining step. That means the rate of the reaction is depends on concentration of only ester. Okay, that's why in rate determining step only one species is involved, that is a protonated ester, and that's why this AAC1 is a unimolecular reaction. Unimolecular reaction, and this reaction is also a first order reaction. This reaction is a first order reaction. So unimolecular reaction gives said based on the molecularity of the complex reaction and the order of the reaction that we can determine by the experiment. Okay, so this reaction is a first order and the molecularity of this reaction is also a unimolecular reaction. Okay, and the second step, this is the first step, this is the second step. So this is the first step and this is the second step. So the second step is a rate determining step. This is also second step. So second step is a rate determining step. Is there any doubt in this mechanism? Anyone wish to repeat this mechanism? Any step that you could not understand? Any step that you could not understand? So what we have discussed here is ester hydrolysis, but through the AAC1 mechanism. And AAC1 mechanism is always followed by those molecules which are able to form a stable carbocation. That's why here I take the example of sterically hindered methyl macetoate. Methyl macetoate. Is there any doubt in this mechanism? Is there any doubt in this mechanism? You can take the screenshot. Later on, if you have any doubt, you can tell me in the next class. So in AAC1, yes, it is acid catalyzed. Yes, it is acid catalyzed. Which bond is break? Acyl oxygen. Yes, this bond is break. If you look at acyl oxygen bond is break. Yes, this bond is break. This is acyl oxygen bond is break. Unimolecular, yes, it is a unimolecular because this is a rate determining step. And rate determining step involves only one species, that is ester. So molecularity of this reaction is a 1. That's what is a unimolecular. Okay, so order and the molecularity both are different concepts. Order that can be determined by the experiment, and the molecularity of the reaction can be determined by red determining step. Okay, if in red determining step only one species is involved, that is a unimolecular. If in red determining step two species are involved, that is a bimolecular. This is a molecularity of the reaction. And order is somewhat different concept than the molecularity. Molecularity is a theoretical concept. We can see the reaction mechanism. We can tell that it is a unimolecular or bimolecular. In order to determine the order of the reaction, we have to carry out the experiment. Okay. Is it clear? Is there any doubt in this mechanism? Is there any doubt in this mechanism? Shall we move further? Shall we move further? Yes or no? Okay. So next, that is similar to this mechanism, that is esterification. Now we are going to discuss the esterification. So earlier that we have discussed is a ester hydrolysis, and now we are going to discuss is a esterification. Of macetoic acid. Okay. So we are discussing the esterification. Okay. So let's discuss first macetoic acid. So this is our macetoic acid. It is 2,4,6 trimethyl acid. So this is a macetoic acid. And this esterification of macetoic acid, we are going to explain through the AAC1 mechanism. AAC1 mechanism. Okay. So the first step, what happened in presence of acid? Because it is acid catalyzed. Now, this oxygen contains two lone pairs. One of the lone pair get protonated, gives a protonated acid. Gives protonated acid. Now, one of the lone pair is used for the protonation. That's why these oxygen become positively charged. And still, one lone pair is left on this oxygen. So the forward reaction, of course, is a protonation. And protonation is always fast. But what about the backward reaction is also deprotonation? Because when I remove the proton from here, we get this macetoic acid. So that is the reverse step is a deprotonation. So by elimination of H plus, we get macetoic acid. Now, again, see this. This is a good living group, water molecule. So this is a good living group. So it can easily eliminate from the molecule and forms a stable carbocation. So later on we will discuss why this acylium ion is stable. As I said earlier, this acylium ion that is formed is stabilized by two effects. One is mesomeric effect and another one is hyperconjugation. I will discuss in detail after the completion of this mechanism. Okay, so what happened in the next step? So this will eliminate easily. This will eliminate easily. What it forms? A stable acylium ion. Stable acylium ion. So by elimination of water molecule here, by elimination of water molecule. So elimination of water molecule and the formation of this stable intermediate is a rate determining step. So in rate determining step, only one species is involved here, that is a protonated acid. That's why the esterification is also a unimolecular reaction. Esterification is also an unimolecular reaction. Okay, but what happened in backward reaction? Backward reaction, what happened? Water molecule is attacks on this carbon because oxygen has two lone pairs. So one of the lone pair now attacks on this carbon, we get this structure, but this is a fast step. This is a fast step. Is it clear? Let's see what happened in the next step. Now the methanol molecule attacks on this carbon and what it gives? Protonated ester. Here what happened? Methanol, in methanol, oxygen contains two lone pairs. Now one of the lone pair now attacks on this carbon and gives this protonated ester. So the attack of this methanol on this carbocation is a fast step. Similar to here. The attacks of the water on this carbocation is a fast step. And what happened in the backward reaction? The methanol is eliminated. So in the reverse step or in backward step, what happened? Methanol is eliminated and this is a slow step. This is a slow step. Okay. The last step, what happened? Deprotonation. The last step, deprotonation. Elimination of minus H plus. Gives ester. So this step, this proton get eliminated. So this step is a deprotonation. And backward step is a protonation. By adding the H plus, we get this step. The backward step is a protonation. In both steps, are fast. And our product, that is methyl mesitoate. Again, if you observe the second step, this is a first step. This is a second step. Again, the second step is a rate determining step. And if you observe in rate determining step, only one species is involved. That is a protonated acid. It is a protonated acid. Okay. So the second step is a rate determining step. Means that is talking about esterification. That means the rate is depends on concentration of acid. And if you observe, only one species is involved in rate determining step, that's why it is a unimolecule. And the order of the reaction is a first order reaction. So this is a experimentally determined that esterification is a first order reaction. And this is a theoretical concept, means the molecularity is a theoretical concept. So in case of complex reaction, we have to see the rate determining step. If one species is involved in a rate determining step, it is referred as a unimolecular reaction. If two species are involved in rate determining step, it is referred as a bimolecular reaction. Again, I said the order of the reaction is an experimental concept, but the molecularity is a theoretical concept. In case of elementary reaction, order is equal to the molecularity. But in case of complex reaction, we have to see the rate determining step. Is it clear? So this is about AAC1. So in this class, we have discussed about the ester hydrolysis and esterification through the AAC1 mechanism. And the beginning, I told you that only those molecules are proceed to the AAC1 are able to form a stable carbocation. In the both case, we have taken the example of sterically hindered molecule. In case of ester hydrolysis, we have taken the example of methyl mesitoate. And in esterification, we have taken the mesitoic acid. Both are able to form stable carbocation. Okay. So today we are stopped here. In next class, we will continue with this mechanism. And in next class, we will discuss about the RDS of both of these reactions and why this acylamine is stable. Okay, clear? So is there any doubt in this mechanism? Is there any doubt in this mechanism? Is there any doubt in this mechanism? So what we have discussed today, it is also available in my YouTube channel. So whenever you get any problem, you can refer the video and you can ask your doubts in the next class. Till then, thank you very much, all of you. Have a nice day. Thank you.